So we want to start bringing back some skills that we learned in the last unit, or actually the last 2 units. We want to start looking at the concept of net force. We want to start looking at vector addition once again. We're going to give it a special name though. If you take all those vectors and you kind of add them together to see that overall effect, this technique is actually referred to as superposition. So let's look at that. Don't worry about the word superposition. It's basically what we've been doing this whole time. So we're going to see how we can do Newton's law of universal gravitation in the context of more than 2 objects interacting. So we have a coincidental timing of the celestial bodies. So we've got the Sun, Earth, and Jupiter. They're all aligned in the same plane. So they're going to form a straight line. So we're going to use this data from the chart below. We want to find the net gravitational force exerted by both the Sun and Jupiter on Earth. Let's have a little bit of a drawing of this. Now, I'm not going to draw a great solar system, but hey, it is what it is. So let's draw, I probably should have wrote the word sketch. But okay, here's the Sun. Here's the happy little planet Earth. And I don't really have a red pen, but here's Jupiter. Definitely not to scale. So this is what we have going on. We have Earth in the middle of these 2 planets, and we want to find the net force on it. Keep in mind that the force of gravity is always attractive. So Earth is going to be attracted towards the Sun, and it's also going to be attracted towards Jupiter. What we want to see is what is the net effect on that. Now, full disclosure, we are simplifying the living hell out of this question. First of all, Newton's law of universal gravitation is a bit of a simplification. It's not the whole story. But more importantly, we're ignoring the rest of the universe. We are assuming in this universe, it's the Sun, Earth, Jupiter, nothing else. It's a bit of an issue, but again, our results are still pretty decent broad strokes. Now, if I look at a free body diagram for this, so for my FBD, and we're drawing this from the perspective of Earth because Earth is the thing that's we're trying to find the net force on Earth. So, because of the Sun, there's going to be a force of the Sun on Earth that's going to be directed towards the Sun. So Earth is going to be pulled on towards the Sun. At the same time, Jupiter itself is going to pull on the Earth towards Jupiter. So Earth is being pulled towards the Sun and Jupiter. Let's find out the effect on this. Now, for positive convention, let's call towards the Sun positive. Now, we are going to need to find 2 forces of gravity. We are going to need to find the force of gravity between the Sun and the Earth, and that between Jupiter and the Earth. So let's do that. So first of all, the force of gravity for the Sun and Earth, it's going to be G times the mass of the Sun times the mass of the Earth divided by that Sun-Earth distance squared. This data has to be provided to you. Except for the Earth stuff, Earth data is on the data sheet. Anything else will be provided to you. In your workbook at the very back, there's also a table of planetary data. But on exams, you will get that. You do not need to know this by heart. So we got our universal gravitational constant. We have the mass of the Sun. And then we also have the mass of the Earth. And then we are going to divide that by the distance between the Sun and the Earth, which is going to be that 1.50 times 10 to the 11 meters squared. So what that's going to give us, let's see here. We'll just be really careful with our calculations. So the big mistake made here, there's a lot of numbers, a lot of scientific notation. Be really careful with punching stuff in. And of course, always don't forget that square there. That's always the big culprit. So we're going to get about 3.5218 times 10 to the 22 newtons. Now this is directed left, so we're going to leave that as a positive number. The drawback with using the FG formula, Newton's law of universal gravitation, it only deals with magnitude. It will never give you the negative sign if you need one, so you will have to put that in. We'll show you what I mean by that in a second. So the force of Jupiter on Earth, if we want to find the magnitude of that, we're doing G times the mass of Jupiter times the mass of Earth divided by that distance between them squared. So once again, we're going to put in all these numbers. We have a lot going on here. So the mass of Jupiter, we're told it's 1.90 times 10 to the 27 kilos. We want the mass of the Earth here. And then we're going to divide that by that distance between the Earth and Jupiter, which is provided in the data table. So we get that 5.88 times 10 to the 11 meters, and then we're going to square that. So let's see what we have going on here. And then we want to put in this. So what I'm going to get here for this is I'm going to get it's about 2.188 times 10 to the 18 newtons. Now, this is the thing that we have to watch for. This is a drawback of the law of Newton's law of universal gravitation. It doesn't have negative signs built into it. You have to put it in. Because if I go back to my free body diagram here, I can see that the force of Jupiter on the Earth, it's going right, and we've called left positive. We have to put that negative in here. So this is going against positive. It's a bit of a drawback, so we have to be really mindful of that. We have to put in that negative. So please watch, be very careful when you're doing these Newton's law of universal gravitation questions. So then the last thing is, we're just going to kind of put this on the side. So then the net force, it's going to be that force of gravity because of the sun on the Earth, plus that force of gravity of Jupiter on the Earth. So we found for the sun, we got that 3.5218 times 10 to the 22 newtons. And then to that, we're going to add, again, we want to have that negative because it's counteracting here. So with that negative 2.188 times 10 to the 18 newtons. Notice that there's a 4 order of magnitude difference. What that's telling us is that this force of gravity between Jupiter and the Earth, it's almost inconsequential compared to that of the sun and the Earth. The sun is really going to win this battle, but the sun is also significantly more massive, so that shouldn't really come as a surprise. So magnitude-wise, we're going to say it's about 3.52 times 10 to the 22 newtons. Now, it didn't say find the magnitude, it said find the net gravitational force. So our force is positive, we said towards the sun is positive. So the last thing that we could say here is that the net force, it's about 3.52 times 10 to the 22 newtons. And then for direction, we'll just say towards sun. That's about all we can say. So this idea of adding up forces using vector addition, it hasn't changed any, just you have to be aware there is a drawback of using the Newton's law of universal gravitation because its calculations deal strictly with the magnitude of Fg. So you have to be very careful with any placement of negatives.